All right, so our team is very excited to be sharing our work on comparing the performance of Spark and Dask for Amazon product reviews analysis. This is a little agenda for our presentation. So when we were originally searching for large data sets for this study, we were confident in choosing Amazon product reviews. As many of you probably know, Amazon is one of the largest e-commerce platforms there is in the world today. Also, a lot of previous work has been done in terms of analysis of product reviews, but these previous works take more of a qualitative approach, with the main method being sentiment analysis. So our team wanted to take more of a quantitative approach where we strictly focused on product ratings, number of reviews, and also product retention, which we measured by how many months did the product continue to receive reviews. Additionally, the Pandas module in Python is one of the most popular tools utilized in the world of data analytics today. So aside from gaining insights on this data set, our team also wanted to address another important topic, which is what are the limitations of using Pandas for big data processing and analytics? And how do alternative solutions like Spark and Dask compare in addressing these limitations? So a little bit about our data. We definitely weren't wrong about Amazon data availability because we actually had to scale down our data set from 29 categories to 5 categories. But even then, that still left us with 40 gigabytes of data. So you can imagine how large the data set would have been with all the categories included. And the reason why we decided to scale it down is because of some AWS Academy's instance type restrictions and some worries of processing limitations. But nonetheless, with this big 40 gigabytes worth of data, we attempted to process it through Spark and Dask, and we were curious to see how well these two big data systems could handle it. So we took lots of notes of performance along the way.
Okay, hello, I'm Hyun, and let me do a quick overview of our data set. And I added plots of showing interesting insights of our data set. So first of all, the mean review lengths vary by product categories. Notably, reviews of books tend to have lengthy reviews because it is normal to find some passionate book lovers posting long and exclusive reviews, such as how much they love the author and show how they felt after reading this book, and this is presumed to be found in this plot on the left. And for mean upvotes, books and electronics tend to have received many upvotes. And interestingly, book lovers also tend to share detailed reviews, but also were interactive with each other by hitting a lot of upvotes to other reviews. Yeah, on the other hand, for our response variable, the mean distinct months, there was no notable difference between categories. All of them stayed on the market around 10 months. Yeah, then for summary statistics, the raw data set of reviews with 55 million rows can be summarized in terms of ratings, review length, and votes. Here, overall reviews were pretty generous. Both the mean was 4.34 and the median was 5. However, there was huge standard deviation in terms of review length, as you saw on the plot from the previous slide. Also for votes, most of the reviews did not get any votes at all, and the median of 0 displays that. The largest vote was largest vote a review got was 999. Okay, on this plot, we used the condensed data set aggregated by products. And it is unsurprising that average ratings, reviews per month had low standard deviations based on the information that I shared earlier. However, the total reviews, total votes, and average review length had higher standard deviation varied by products.
Thanks, Hyun, for that EDA. So we have the details of how we set up our project here. And essentially, our first step was making use of 5 AWS EC2 instances, virtual machines to use as workers and to run the code. And then HDFS was used in this project to store the raw files. And then lastly, Apache Spark and Dask was installed across all virtual machines. And in general, we assigned 2 workers to each of the 5 cores. So in order to benchmark performance, our group had to code identical implementations for both Spark and Dask. And although Spark and Dask are generally used for different cases, they can be used in the same data pipeline, which benefited us greatly. So when initially attempting to load in the JSON file format that the Amazon reviews were in into Spark, everything ran smoothly. But when attempting the same in Dask, we ran into the constant error of workers dying, which we believe was related to the memory limit. But we learned that Dask employs a partition-based method for reading JSON files, which helps to divide the data into smaller and more manageable chunks. So we thought we had found a solution in which we tuned the partition parameter, but doing so actually introduced a new problem in which there were instances where the metadata was inaccurately inferred due to the limited availability of only the first partition of the data or the first few partitions, which resulted in incorrect data processing. So then we developed this data pipeline to help us address these problems, and the general flow is as so. We loaded the JSON file into HDFS, then cleaned and aggregated the data through Spark, exported those clean data sets in a CSV format, and then loaded these files into Spark and Dask for analysis.
Yeah, then some of the techniques we use for Spark, as mentioned, when we're loading in the JSON, we wanted to keep the file size as small as possible. So we had to just pick the features that we would use for the analysis. So we did this using the PySpark struct type. But then for the other aggregation, other functions, we use the regular PySpark functions. And for regression, we use the PySpark ML library, which comes with Spark. And then for Dask, we had to make use of a bit more, got a bit more creative with processing these things. So one of the things we did was made use of Dask's distributed client, as you see in the code snippet here. So this was used when we were doing aggregations, because when we tried doing aggregations on without using the client, using compute, it gets loaded into memory, which overloads the workers. So another thing is we had to convert the data to Parquet files, which are more partitioned, so that we could properly do the aggregation. And as you see in the code snippet on the side, that's where we did the aggregation using the distributed client. And for the regression libraries, Dask also has a Dask ML library, which we just had to install as well. Then for our analysis, there's a breakdown of what we did. So as the data was discussed earlier, we had the 55 million rows of review data with the numeric features there. And then for products, you have 1.5 million rows. So for the models, we did logistic regression and linear regression. For logistic, we focus on the product data, the 1 million row data set, where the binary response would be if a product has over the median distinct months in the data set. And then for linear, we wanted to see if we could use rating as a response variable and to see if the other numeric features has some correlation with it. So just some modeling details, we used some standard procedures. We split the data 80-20 for training and testing data, and we used standard scaling implementations, which are both available in Spark and Dask. So we have some code snippets here just to show how the pipeline worked for both Spark and for Dask. Now going to the results, the first thing we wanted to check was the performance comparison. So we split the process into these different parts. As we can see, for feature engineering, Dask slightly outperforms Spark, but when you go to more computationally heavy processes like summary statistics, data aggregation, and regression for a smaller data set, we can see that Spark outperforms Dask here, where Spark finishes in less than a minute. Dask usually takes 2 to 4 minutes for these things. And then interestingly, you can see in linear regression, when we used the 55 million row data set, Spark finished in about 2 minutes, while Dask took 53. So there's a lot of possible reasons behind this. When we were running it on Dask, we saw that the workers were experiencing like worker unresponsive errors. So since the workers are unresponsive, Dask would try to reassign the task to other available workers, and that would have its own set of overhead because of network issues, which could possibly lead to this extended runtime. Then for our model results, for logistic, we mentioned we're using the distinct months as a response variable. So we did two models. The first one, we used the intuitive idea that products with more total reviews, total reviewers would have total months. For that model, expectedly we got high accuracies of 90 plus. And then for the second model, we used totals normalized by months. So this is so that we can take out the bias for products which have been on the platform for longer. For here, we got accuracies in the 60s, but we still believe it's a very promising result. And then for linear regression, we used review length and votes as features. So RMSE is pretty good, but as you can see, R squared is not great. So we can see that as you'd mentioned earlier, most of the reviews are already high. So it's already, the median was already 5. So since the data is skewed, that could be a reason. And also since review length can be erratic, using it without other features can be hard to predict features, rating, I'm sorry. So also something to notice, Spark and DAS tend to have slight differences in the accuracy that they give. So this is possible due to the implementations in their various libraries. And then we also did a scalability comparison. So we mentioned we were running both Spark and Dask on 5 workers each. So we did, instead of 5, we did 1, 2, and 4 workers. So as you can see, every time the workers increase, the performance in wall time usually goes down by a factor of 2, so it gets divided by 2. You can see that in the summary statistics, data aggregation, logistic regression, and linear regression. So for DAS, since it took 53 minutes in the full version, we saw that it was not crashing. So we weren't able to compute the final runtime due to time constraints, but we can see that it wasn't crashing the system. So it's still effective way of doing it.
Okay, as part of the conclusion, we have some goals accomplished. Firstly, we were able to gain a deeper understanding on the implementation of distributed system and figure out how it increases our performance when dealing with large data sets. And secondly, we implement direct performance comparison between Spark and Dask. And in terms of data wrangling, Spark did a better job than Dask on our data set. However, when it comes to data modeling, although there was a slight difference in total amount of time, both Spark and Dask were able to successfully finish data modeling. And third, we implemented a scalability test to identify optimal resource settings. And by scaling down the virtual machines, we were able to identify the decrease in performance, which could later help provide insight in choosing the appropriate system for different use cases and optimizing the use for cost and time efficiency. And lastly, we conducted quantitative analysis on Amazon e-commerce products. And for future work, we hope to try different types of EC2 instances, dataset, and complex models. And on AWS Academy, T3 large instance type was the largest instance that we could use. So we would like to know if the results would be different if we tried memory or calculation specialized instance types rather than T3 large. Also, although Spark performed better in our dataset, in some cases, Dask might perform better. Therefore, we cannot naively conclude that Spark works better than Dask for big data sets in general. Also, since we drop the complex metadata column mostly comprised of text and use only numeric columns, we would like to know how complex machine learning or deep learning models would perform under different types of data. And lastly, we were not able to figure out which caused the differences in accuracy for the same model between Spark and Dask. And in order to figure it out, we should investigate the different architecture of machine learning library within Spark and Dask. All right, this is it for our presentation. Hope you enjoyed, and thank you.
Thank you so much, everyone. We hope you enjoyed.